a little bit about motion. And first thing I wanted to do was sort of put some things in perspective for you, and then I wanted to get into some terminology. But it all started, a lot of our physics research started with Aristotle. Right? That was 350 BC, approximately. 350 BC. And Aristotle had some problems. He couldn't get past the fact that friction and air resistance influenced everything. And so a lot of his ideas about motion were wrong. The foundation is wrong, right? And when the foundation's not right, you can't build a strong house on that, right? So a lot of his ideas were wrong. And people really revered Aristotle. They believed him and really revered everything he said, and they stuck to his ideas for a long, long time. It took almost 2,000 years. Not much progress was made over that time period in physics because we were stuck thinking about things the wrong way. Then in around 1600, 1630, Galileo came along and changed some of those views and said that, gave us some different ways of thinking about things, introduced the idea of inertia, and that enabled all kinds of things to happen. Once he did that, Newton came along right afterwards, came up with his laws of motion, and in the next 200 years, all kinds of advances. So you've got to get the foundation right? Because you're building on that. Just like in math, you got to get the basics down so you can do more complicated things. Same is true in physics. And we were stuck thinking about things the wrong way for a long time. Galileo came along, straightened us out, then Newton, and a lot of progress was made. And that's where we're going to start off with motion. And one of the things that we have to deal with in physics is the fact that our terminology in physics is very precise. We know when a physicist says a certain thing, velocity, he or she knows exactly what that means. But in everyday usage, right, we use the term velocity a little looser. Right? We use terms a little looser. So we have to get used to that. Velocity is one of them. Position, distance, displacement, speed, velocity, those are all terms that we have to sort of come to grips with and figure out how we use them in physics as opposed to everyday usage. All right, so the first thing we want to talk about is position and displacement. So somebody has a particular position, and we could define that with a vector. Let's say we have an xy plane here, and there's our position. We can define that. That's its initial position. I'll put a little I there. And then the person or thing moves to some final position. Maybe they end up over here. And so we can define that as some final position. So that arrow, that vector, it has a length and it has a direction, right? So it's a vector. And it defines our starting point, it defines our ending point, our initial and our final place. So the position is just where we are at any given time. So displacement is the change in position. Okay? So we would use maybe a delta R. We usually use delta x, but that sort of implies one direction. So delta always means final minus initial. And when you do vector, we're going to do this in lab next week. We're going to go over vector addition and things. But let me just show you real quickly. If you're doing, our final vector looks like something like this. Gesundheit. That was our final vector. And our initial vector, was up sort of at this angle. But what we want to do, we want to subtract our initial vector. So how do we do that? Well, we can add the opposite, right? We can add the inverse of our, or the negative of our vector. So this is the opposite of that. That would be minus our initial. And when you add vectors, they're tip to tail, right? So you start at the tail of the first vector and you end at the tip of the last vector. And our displacement is the red line there. That's supposed to be a straight line. So that's the displacement, right? It moved to the right by a certain distance. Right? That's what happened. The point moved to the right by that distance. So that's the displacement. That makes sense. Started at one point, ended at another point. Displacement. What about the distance traveled by our object? How do we know how it went from our initial place to the final place? It may have taken the, let's see, the blue path, or it may have taken the green path, or it may have taken the red path, right? We don't know how it got from the initial place to the final place. And each one of those paths has a different distance traveled, but they all have the same displacement because they all begin and end at the same place. So one of the ways to think of this is you go for a jog, right? Exercising, leave your house, you go for a nice jog. Where do you end up? Back at your house. What's your displacement? 0. Started and end at the same place. A basketball player starts at center court, runs back and forth for an hour and 48 minutes, whatever, for 48 minutes, right? Back up, down the court for 48 minutes. Ends up roughly where they started. They had a huge distance traveled, right? They went back and forth a bunch of times, but their displacement, almost nothing, right? They end up basically where they started, no displacement. So those are just a couple of examples of how we use terms here in versus everyday usage. And then the other one is speed and velocity. So speed is a scalar quantity. So we would say something like 50 miles per hour. That's a speed, right? 50 miles per hour. Velocity is a vector quantity, which means it has both magnitude and direction. So 50 miles per hour due north. If you drove 50 miles per hour due north, that would be your velocity. If you just said 50 miles per hour, you're giving me the speed. And the speed, the average speed, is the distance over the time it took. And the average velocity is the displacement over the time it took, because it has direction associated with it. So if you go out for your jog and you run at, what do you run at? 4 miles an hour, 5 miles an hour? Is that a fast run? I'm not a runner. You go out for your run, straight line from your house, 4 miles an hour for half an hour, turn around, come back 4 miles an hour straight back toward your house for half an hour. Your velocity, because it's a vector quantity, has direction associated with it, half the time pointing this direction, half the time pointing this direction, it averages to 0. And you end up back where you started, right? You didn't go anywhere in the hour. You started and ended at the same place. Your average velocity is 0, but your average speed, 4 miles an hour over the whole thing, right? You were always moving at 4 miles an hour. Okay.